Hello there and welcome to this next computer science video. In this series of videos we're going to look at the topic 1.2, which is software and software development, and this is for the H446 specification from OCR, which to me and you is A-level computer science. Now, I decided to split this topic up into multiple different videos because I thought it was unfair to make you sit through 2.5 hours of computer science straight talk. So we're going to break it up a little bit. In this video we're going to talk about topic 1.2.1, which is system software. And that covers the need for, the function and the purpose of operating systems, memory management such as paging and segmentation and virtual memory, ISRs or interrupt service routines and the role within fetch, decode, execute cycles, and then we've got the scheduling algorithms. We move on after that to distributed, embedded, multitasking, multi-user and real-time operating systems. We look at the basic input-output system. And we've got device drivers and then virtual machines at the end of that. So we're going to dive straight in and get stuck into operating systems. Now, when we say operating systems, it's actually a piece of software that manages the communication with your computer hardware. It's like the middleman in between us and what we're doing to the computer and also what the computer's actually doing to the hardware. So that's the operating system. Now the bootloader in read-only memory loads the operating system into RAM when the computer is switched on. And that you might remember that RAM is volatile, so it forgets everything when there is no power, whereas ROM is non-volatile, so it will keep an idea of what firmware is stored in there, and then that's where the bootloader comes from. The operating system manages the hardware and provides an interface for the user and the application software. But if you're as old as I am, you'll remember that operating systems didn't always have nice graphical user interfaces. So, what is the point of the operating system? Its function is to provide a user interface. It deals and handles memory management. It will handle interrupts from different devices, internal and external or peripheral devices, and also processor scheduling. And you can see there the user is the first left-hand side box. It uses something called application software in order to interact with the operating system, and then the operating system decides what to do with the hardware. We can bypass application software and deal directly with the operating system, which then interacts with hardware. And you'll notice that those arrows are bidirectional, so they're working both ways. And that's true of our computer system. So let's talk about the operating system interfaces. We've got the nice, pretty, graphical user interface that me and you are used to. It's user-friendly. So you don't need any training, and it's easy for beginners to use and understand. Discoverability, so visual options, help the user find features, and they can trial and error by clicking, dragging and dropping. Also, what that does is it reduces the errors made on your computer because you don't need that technical skill. You're not writing on the command line. You're not writing in lots of commands. You are using your mouse to interact. So what about accessibility? Well, accessibility has been massively improved because anybody can use a computer now pretty much, and it supports touch and mouse for wider usability. So that's touch screen is what it's talking about there. Whereas if we look at something which a lot of people actually do in the world, and that is Linux command line programming, for example, or using the terminals, you have CLIs, which are called command line interfaces, and they are much more powerful. The speed is much quicker, and for experienced users, they can make pretty quick work of most tasks using the command line. If you're the sudo user, then you will have lots of rights and lots of power to do lots of things that you need. And it uses minimal system resources because of the graphics aren't there using lots of processing power. Now, think about remote access for a second. It's ideal for remote management over secure connections because of the lack of heavy lifting that a graphic user interface might require or provide. So, memory management then. Programs and their data, they need to be loaded into RAM first. And we know that, or we should know that. The operating system must manage the allocation of random access memory to different programs, and different programs require different amounts of RAM, and during the fetch, decode, execute cycle, RAM is used in different ways and different amounts of storage is used. So they may not be sufficient RAM for all desired processes to be completely loaded into RAM at once. So what do we do if that happens? What do we do if we run out of RAM? Well, the first method is paging. And paging divides memory into fixed size blocks called pages. And the process here is that each process that we have in our computer is split into pages that can be loaded into any available frame in memory, allowing a non-contiguous storage. And what that means, that's an interesting word, non-contiguous. That just means things aren't stored one after another. They can be stored anywhere you like. And the advantage is it reduces fragmentation and allows efficient use of memory, but it can cause internal fragmentation due to fixed page sizes. So, for example, code can get chopped and split up, which then requires the processing to bring it all back together. And over time, things can get fragmented more and more. And in modern machines now with lots of memory and lots of random access memory, that can be even more of a problem. The other method is usually the one we try and go for. This is segmentation. It divides memory into variable size segments based on logical division. So in your exam, when you're talking about paging and segmentation and comparing them, paging is fixed size blocks, segmentation is logical divisions. So them logical divisions can keep functions and arrays and objects together, and the process is that each segment is stored in a separate part of memory which allows segments to grow or shrink dynamically where needed. Now that does take a little bit of extra management, but the advantage here is that it reflects the logical structure of a program, making memory management more intuitive. The downside is it can lead to external fragmentation, as variable sized segments do leave gaps, and we can't always fill them gaps up because of the variable nature of these programs. So let's look then. Here's two identical pieces of RAM, or it seems that way. And in paging, we take our random access memory and we split each part of RAM up equally. You can see that they're all the same size. We've got program A and program B and program C, and we've managed to fit all them in. You'll notice that program A is split up in between program B, but everything does fit. In segmentation, logical splitting of RAM, with the tasks being placed where they best fit, you can see that we've managed to put program A all together. Program B has smaller sections, so they've gone together to keep the logical nature of B together, and then program C is then shoehorned in at the end, it seems. Now, we do have another method which is called virtual memory. Virtual memory is really, really bad. We don't want to go there, but a computer that has a fixed amount of RAM demands memory. When we exceed the amount of memory required, then we can cordon off basically an area of the hard disk, and that can be designated as virtual memory. So you have reduced some storage on your hard disk, but you will be using it as random access memory. And if you know anything about storage devices and the read-write speed, your hard drive or your secondary storage device is slower to transfer than random access memory, and therefore slower than the CPU itself. And that can cause problems. So some of the pages of current processes are stored in virtual memory until they are needed, at which point they are swapped into RAM. And if you were to use your logic here, you would say, well, the least frequently used programs should be stored in virtual memory, because we don't want to be going backwards and forwards between our secondary storage device trying to access them. You do get an increased memory capacity, so your processor can continue to execute tasks and not get bottlenecked as much. However, your performance will be slower. So repeatedly swapping pages in and out of virtual memory can noticeably slow down the computer. And that's because the processor can sit idle waiting for a slow process to be moved from secondary storage, virtual memory, over to the processor. And that is an issue. This is known as disk thrashing, which I mentioned in the previous video. So what about interrupts? Interrupts. If I was to interrupt you, then I would be stopping your conversation potentially. I get interrupted about 3 million times a day. In class, students want to ask me questions, and then they will just cut me off halfway through an explanation, and then I would answer the question and carry on. Okay? One way of dealing with that is to get people to put their hands up. Then I can see who's patiently waiting and then select the people and go along with it. Interrupts are much the same in terms of what we do in there. So sometimes we do need to interrupt the processor because we have a more burning issue, a higher priority task. We have an interrupt command to do this, and lots of devices come with inbuilt interrupts that interact with your operating system. Software and hardware can send interrupt commands, so some examples that you might need for your exam are things like an input or output device sends an interrupt signal and needs attention. The printer runs out of paper and needs to inform you. An error occurs in a program and it has to shut down. A scheduled interrupt from an internal clock, and then a power failure. So, if we think about those kinds of interrupts, they'll happen quite frequently across your computer. But the CPU will check at the end of each clock cycle whether there are any interrupts to be processed. So if we start off on our computer and we are fetching, decoding and executing instructions, your processor is going along no problem. It's happily working away. After the execution phase, it will say, are there any processes that have generated any ISRs, interrupt service routines? If it's a yes, then what do? We then transfer control to the interrupt handling the program. That's a very, very, very abstract way of looking at it. There's lots more complication going on there, but for A level, all we need to know is that when an interrupt service routine is raised, it is dealt with at the end of the execution phase. We'll deal with the actual interrupt itself so that we can get on processing our instruction. Now, if those three instructions there, or those three processes, the fetch, decode, and execution phase, if they get cut short, we need a way of tracking where they were up to, because we will transfer off the current process, we'll run the interrupt service routine and work out what the processor needs to do. We'll process something that's come in and needs processing, and then we will go back to what we were doing before. So we have a data structure to handle that process. And that data structure is a stack. So interrupts use a stack in order to take off the current process and basically press pause. So when an interrupt is detected, the processor stops fetching instructions and instead pushes the current contents of its registers onto a stack. And that is the pause button that we're pressing. The CPU uses an interrupt service routine to process the interrupt. So there's our stack with task 1 and task 2 on it, and there's our CPU with task 3 on it. So a little bit of memory recall here. We just need to recap what a stack actually is if you've forgotten. So some stack rules. A stack is a first in, last out data structure. We can only push things onto the stack from the top. And we can only pop items off the stack from the top also. So it's a perfect way to keep the order of our tasks. So where would task 3 actually go? Well, it's sat on the CPU at this current process. So now we look at our stack. the CPU was running task 1 and that got interrupted. So we pushed task 1 onto the stack. The stack was empty. So it gets pushed into position 0, let's say. Task 2 was loaded into the CPU and this was then interrupted and pushed onto the stack. And that means it goes on top of task 1. And that's because it's a first in, last out data structure. Task 3 is now in the CPU getting processed, and when task 3 finishes, task 2 will be popped from the stack back onto the CPU, reloaded, all the registers are reloaded, and it can finish processing. When task 2 is finished, task 1 will be popped from the stack and loaded into the CPU to finish processing. So jobs remain in order on a stack. And I've seen exam questions in the past talking about this process and how a stack might work in terms of practical examples. So what about a browser? When you go back on a browser or forward on a browser, or you press undo or redo, all of that is on a stack because a stack is a perfect data structure to keep the order of things. Now interrupts have different priority levels. Some are far more important than others. So, interrupts have different priorities and will be processed in order of priority. Interrupts can themselves be interrupted if the new interrupt is of a higher priority. If a higher priority interrupt occurs whilst the interrupt is being processed, the original interrupt registers will be pushed onto the stack as well. So what kind of interrupts would be the highest priority? Well, if you press the power button on your computer's going to panic and it's going to go, oh no, we need to save everything quickly to secondary storage so that we don't lose anything. And you might have been on a Word document or a PowerPoint or something, and it might have auto-saved because the power's been lost or something like that. And you thank your lucky stars that things have been saved. And that is where a high priority interrupt like quickly save will happen. Let me give you another example. There's our stack and there's our CPU. Take me for example, John. There I am. I sit on the bottom of the stack. Okay, why am I on the stack? Because I've been bumped off the CPU because who has a higher priority than me? You guessed it. It's the king. He's obviously got a higher priority because he is the monarch of the country and I am just a lonely computer science teacher. So as the king has a higher priority, he gets the processor and he gets to run the processor and use all the time. I get stuck on the stack until he's finished, basically. So let's talk about processor scheduling then. We know our scheduling algorithms, and these are popular exam questions in OCR's exams. So a single CPU can only process instructions for one application at a time. It's true, isn't it? Fetch, decode, execute, fetch, decode, execute. So the operating system must schedule when each application can use the CPU. Now I'm talking very basic stuff here, a single core processor. This gives the illusion of multitasking. And what that is the illusion that applications will be running simultaneously, but it's not. It's swapping things out in and out the CPU extremely quickly, and it gives that illusion that you're running more than one thing. What are the aims of processing? To provide an acceptable response time to all users, to maximize the time the CPU is usefully engaged, and also to ensure fairness on a multi-user system. Let's look at our scheduling algorithms. And if I was a student here, these would all be on my flashcards, and I'll have my description on the back and my word, my algorithm on the front, and I'd get someone to test me week in, week out about what these algorithms do. You may get asked to compare them. It's definitely worth knowing. I've put little images down there to try and prompt your memory in terms of what these scheduling algorithms are. So let's start off with round robin. So a round robin is when each process is given a fixed time slot in a rotating order. Fair for all processes, but can lead to high overhead with frequent context switching. So you may get a small amount of processing done, but then you have to move on. Everyone gets a time slice, and we share the processing power, which can take a long time to get anything done, which is annoying. So let's think about first come, first served. Processes are executed in the order they arrive. So first one there is the first one to be processed. Second one there is the second one to be processed. It's simple, but it can often cause long wait times for later processes. Especially if you've got a big queue, you'll be waiting a long time to get anything done. These next two students often get confused with. So let's take it really slowly. Shortest remaining time. The process with the shortest remaining time is executed next. So yes, they might be in a queue, but the algorithm chooses the process with the shortest remaining time to be executed. And what that does is it minimizes the waiting time because it gets lots of smaller tasks done, but it can lead to starvation of longer tasks because if shorter tasks keep joining the queue, they're going to get chosen first, and your longer task is going to be pushed further and further back in terms of its priority to be executed. Shortest job first. So the process with the shortest execution time runs next. The process with the shortest execution time runs next. So it's efficient, but can also cause starvation for longer processes. Now, if you were to read those two explanations, you might not be able to differentiate between what the difference is. And this is where students get confused. So, with shortest job first, it runs the job that takes the least time. And once that job starts, it finishes. There is no stopping it. It doesn't change its mind if a shorter job arrives, basically. So, think of it like a queue, right? You pick the shortest person in that queue of height to go next. And once they start to be served or whatever, then let them finish. Whereas shortest remaining time also runs the job that takes the least time, but if a shorter job arrives, it stops the current one and switches to the new one. And this is the main difference. So if I'm serving that smallest customer and a smaller one comes along, don't know why I've gone with height there to be honest, but then we would stop serving, put them back in the queue and start serving the smaller one. And that's the main differences between the two. And finally, we've got multi-level feedback queues. And you can see in the diagram down there, it's probably a better way of showing it, each queue, 1, 2, 3, each queue has a priority. So Q1 is the highest priority down to Q3. So in a multi-level feedback queue, processes are placed in different priority queues based on their behavior and adjusted dynamically. So that's while the program is running. It balances responsiveness and efficiency, reducing the starvation of those programs that have been waiting for a long time to actually be processed. So what we're saying here is, in each of our queues, even though it's based on priority, we will be shifting and moving jobs all the time through the queues. And remember, in a queue, it's first come, first served. So if you're at the front of the queue, you're going to get served first. So there are 5 scheduling algorithms that we need to be aware of for our exams. And now we move on to the different types of operating systems. All of them are there. There are many. What I've done here is I've put down a short description of each of them, because this can get quite confusing. But again, you are expected to potentially compare them all. So distributed operating systems. Distributed. If you distribute something, you are sending it somewhere, right? You are sending it out, outsourcing. So in a distributed operating system, it manages a group of independent computers and makes them appear as a single cohesive system. And that enables resource sharing, parallel processing across multiple machines. You're using them as if they are one. Multitasking operating systems allow multiple applications to run simultaneously by dividing processor time. And that processor time gets divided amongst tasks, and it gives an appearance of concurrent or at the same time execution. Again, an illusion. Multi-user operating systems support multiple users accessing a single system or network resources simultaneously, with mechanisms to manage and protect user data and resources. And I suppose one of the key points to say here is that each user gets their own designated space on the hard drive, their own set of resources, and their own processor time. Or a slice of it. Slice of the processor, should I say. Mobile operating systems, these are relatively new in the world of processor design, but they are designed specifically for mobile devices, providing features like touch support for the touchscreen, energy management, battery life compatibility, and also compatibility with other mobile hardware. Mobile operating systems are designed to be durable, small in size, because they're made for mobiles. Open source operating systems, these are operating systems with the source code is out there. So what that means is if you've got the source code and it's freely available, anyone can make edits, modify, change, or even distribute a new version, often leading to a much larger collaborative development model like Linux, for example. The Linux kernel is one of the best examples of open source code out there that people have adapted over the years. Huge community, lots of experts believing that sharing is caring. Embedded operating systems, specialist or specialized operating systems designed for embedded systems, and they are optimized for specific hardware, like your washing machine, for example. Probably a little bit more technical than that, but they can be used with limited resources. So we see these a lot in things like Internet of Things devices, smart devices nowadays, or even appliances. That could be like heating systems, things like that. And finally, we've got real-time operating systems. And they provide immediate, predictable responses to inputs critical for time-sensitive applications. So think about industrial control systems where we get an input and immediately we have to do something, like a greenhouse. Greenhouse is too hot, open the windows. Greenhouse is too cold, turn on the heater. Right? Immediately that should happen. Things like risk to life systems, traffic lights, autopilot systems, nuclear reactor cooling systems. These are all things that are highly, highly, highly important and cannot fail. Therefore, we need real-time inputs to make real-time actions. So there are all the types of operating systems that could be covered in an exam paper. What about BIOS? The basic input-output system. The operating system controls the hardware and software of a computer system and provides a user interface. The basic input-output system is responsible for loading the operating system when the computer first turns on. It carries out something called a power-on self-test, and it checks that all the hardware is connected and working during this test. You'll hear lots of beeps, or in older computers you'd hear lots of beeps basically indicating whether something's not right. For example, your secondary storage device isn't connected, a keyboard's missing, etc, etc. So the BIOS is actually a really important part of our computer, and that is again gets stored and runs when our computer gets power, basically. Now, what about all the different devices that we have? We plug in lots of devices. I've got lots of devices plugged in right now, to be honest. But device drivers. A device driver is just a small piece of software that tells the operating system how to communicate with that device. So if I'm recording this video on my microphone, my computer has to know how to interact with the external device. And the operating system needs to be able to send commands and also receive commands from said device. And that's what our device driver is. The software is like a translation system. Your computer has to be able to output to a wide range of devices, so the device driver translates the operating system's instructions to print the document into a series of instructions that a specific piece of hardware will understand. Different examples of this, we can have lots of scanners, printers, microphones, I've got headphones, wireless mice, keyboards, you name it. They all have device drivers. Most of the time now you can download them online. You used to get CDs actually. You used to have to install the device driver with a CD. But that's how it works. And even if you come across a device that's a plug and play device, like a USB memory stick, you can plug that in and it'll just work straight away. And that's because computers can come with default device drivers. My Apple Mac's fantastic because it has so many print drivers. I don't think I've ever installed a single print driver on that. Whereas my Windows machine, not so good in terms of that stuff. We move to the bottom now, which is virtual machines. What is a virtual machine? Virtual, not real. So not real machine. Think about it like that. A virtual machine is software that emulates a physical computer, and it allows you to run an operating system and applications in an isolated environment. And that runs on top of another operating system. So while I might be running a Windows operating system right now, I might be able to run an Apple iOS or some kind of Linux operating system, for example. And you can emulate all kinds of devices, laptops, tablets, you name it. You can, mobile phones, you can run them all using a virtual machine. And if your computer's powerful enough, you can run multiple virtual machines. But each virtual machine acts like a standalone computer but shares the hardware resources of the host system. A virtual machine can execute intermediate code, we call it, such as Java virtual machines execute Java bytecode. And that's what it looks like. I used to run a piece of software called Parallels on my laptop, and it would run all kinds of Windows devices when I used to only own a Mac, for example. So we use the word there, intermediate code or words. An intermediate code is generated by a compiler, which is a form of translator, which you should have covered by now. And it's generated by our computer. And that computer has a compiler. And the compiler will create intermediate code as an intermediate step between a high-level source code like Python or Java and the machine code required to run on your machine or your architecture. So it's typically a simplified lower level code that's platform independent, meaning that it can be optimized or translated to run on different hardware. So let's break that down a little bit. We take source code, we then turn it into intermediate code. Intermediate code can be compiled into any designated architecture we want. So if I want to translate it into a Linux architecture, a piece of software will do that for me. Or if I wanted to translate that into a Windows architecture, again, my piece of software will do that for me. So once it's in intermediate code, we can turn it into any designated architecture we like, and then we've got our code and it can run on our host system. So intermediate code, to cut a long story short, is just intermediary. It's in the middle. It's semi-compiled, if you like. And then we just finish it off to the right architecture. And there we are, people. At the end of our video, we've managed to get through 1.2.1 systems software, covering all the different specification points that you can see on there. My advice now is to consider whether you know or you knew all the different parts of that specification point. And I would prompt your teacher to give you some exam questions and have a go at those and see if you can apply some of your knowledge to some form of testing and get some feedback. All right. Join me in the next one for 1.2.2 and we'll soon have this chapter over and done with.